Hi, it's Jim at Top Hat Electronics. I just thought I'd run through some of the work I've been doing to these BSS EPC-780 amps before I put them back together for the final time. I'll start with the simple work to the amplifier modules, the general servicing. So if we look at the underside of the PCB, we can see that some areas have been overheating over time. This area is underneath the driver transistors for the low side, so most of this solder has been reworked, and on one of the modules there was a blown driver transistor which has been replaced. So yeah, basically on the underside of the board it's a case of checking for any dry solder joints, and also here it's not as bad, but they're the drivers for the other side. So if I flip the board over, I can show you some of the work I've been doing to the amp in general. Again, on the preamp, most of this, because it's a single-sided board, most of this solder has been reworked for reliability reasons, and the electrolytic capacitors have been replaced on the preamp. As you can see also on the amplifier modules, I've replaced the smaller electrolytics, and this is one of the drivers which has been replaced previously. I also replaced the bias pots because it was a known failure on one of the other modules. I should mention I've been working on 3 of these amps in total, and also 2 of the smaller models, but I'll only describe what I've been doing through one module. Most of the larger electrolytics, the main power supply filters, don't need replacing. It would be quite obvious if there was issues in this area. The lower voltage for the op amps, just about to see it, this area here tends to get slightly warm. So on 2 of these modules, these have actually been replaced, these diodes and the resistors, but this one's okay, it just needed a bit of solder rework. All the chips which are in sockets have been reseated. This module unplugs, so it can be worked on easier. When it's been put back together, you have to reseal this with Kapton tape to prevent the airflow from just coming out the crack there. What else? Yeah, generally it's a good idea to check the thermal interface between the MOSFETs and the heatsink. These are solid copper heat sinks with, I'll show you the edge, they're sort of copper tree, I think they're called, heat sinks where the airflow is, there's a lot of surface area there. So this is one of the amplifier modules. The other ones did need replacement output transistors on one channel at least, if I remember. This work does go back a few months, so it's actually all written down. Also, a couple of the driver transistors needed to be replaced on the high side on one of the other modules. But generally I'm describing the servicing that needs doing regardless of any, should we say, major faults. I did find that the small signal relays needed replacing on one module, and it might be a good idea to replace these as precaution. I did replace the small signal relays as a precaution on the 760 models because I did find there was more failures in those. Okay, onto the power supplies. This is where the majority of the work needed to be done on 2 of the amplifiers. This is actually, from what I've seen with the 3 amps that are here, there was two different types of power supplies. One I've just labelled as old, which uses Motorola output transistors, which are I've written it on there, 14NK50 devices, which I believe to be the original design. I believe it to be the original design because there's no modification on the controller. On some of the other modules, there's a resistor on the controller chip to increase the dead time for different devices. So should we say the general servicing that's been done to the power supplies, I've replaced the small electrolytic capacitors. On the power supplies which are in a worse condition, I replaced the presets too. And I also I replaced a couple of the sockets, the smaller ones there, which are for the ribbon cable which goes into the controller, the power supply, sorry, for the rest of the amplifier. So this module hasn't had any major repairs. It's still as original, but it has been recalibrated. You can see the general quality of the PCB is quite good despite age. I've actually cleaned it up to make sure there wasn't any obvious issues, and show you the underside of the board to reworked some of that solder on the lower side of the board. And of course this large electrolytic has been replaced on all the power supplies because I found that was a very common fault where that dries up, and that is the snubber, or it's one of two snubbers for the switching. So basically that was a fault area which I'll describe in a minute. Some of this, that's one snubber for the power supply, and the other one's a film capacitor which is across there, which is for the higher frequency. So if we compare that with another one, this is one of the original ones too, which uses the Samsung output devices, IRFP450, and I've been using this one basically as a sort of a golden reference during the measurements. Again, all the same servicing has been done to this one. Show the other side of the board. Again, electrolytic capacitors have been replaced, and this was done by BSS, the 47 ohm modification, to allow the dead time to be increased because the Samsung MOSFETs are faster than the Motorola devices. So yeah, most of this is original. Because it's the other side of the amplifier, the capacitor is mounted on the other side compared to that. Okay, so if we now look at one of the modules which did have catastrophic failure in the output stage, this has been rebuilt. I did decide to use in the end ST Micro 20NK50 output devices. I replaced all of this driver network all as a set, the driver MOSFETs, complementary MOSFET pair, and also the gate resistors and the snubber capacitors and the snubber diodes. I also replaced the insulators. I found it was important to increase the value of the gate resistors slightly to slow down the switching speed of the MOSFETs. These were actually the third choice after some experimentation, and also I replaced, or you have to replace the Zener diodes when replacing the output stage. So it's very important to replace everything as a set, because otherwise you're risking issues in the output. So that work has been done to 2 of the power supply modules, and you can see on the other side too. The gate resistors I did increase to 39 ohms on each leg, which is probably a bit conservative, but it does slow down the MOSFET slightly. I did spend quite a long time experimenting with the switching speeds of the MOSFETs, and that is probably a bit on the conservative side. And also I did increase the dead time resistor to 82 ohms. But I'm measuring the efficiency of this supply compared with the originals, and there isn't much loss of efficiency at all. So I think I'm happy with that, and I'll leave it there. I'm going to show you some testing of the supplies next on the scope, so you can see the switching and the current waveforms and so forth. Okay, so this is one of the 780s under test. I've got one of my rebuilt modules, power supply modules, on the left hand side with the ST micro MOSFETs. That module is suspended, so we can get to the lead out. So there's a current clamp on the midpoint, which is the white lead, so we can measure the current between the power supply output and the secondary side of the power supply. I'm also measuring the VDS on each half of the switch, which is these cables here, which go to differential probes, and I'm also using the provided test point there for the controller clock. So the purpose of this testing is to adjust the synchronization, the clock frequency, and I did base this on the BSS provided test procedure for the 760 amps, according to best judgment, basically, on how far to push the efficiency of the module. So if I briefly divert a minute and just explain some work I did to the auxiliary power supply here. There wasn't really much work needed to be done to this, but I replaced the electrolytics there and just checked it all over and cleaned it up a little bit. Can see on this side, during the failure, the fuse blew on this channel, so can't really see it very well, but instead of trying to force a new fuse into the PCB, I made 2 neat little copper turrets on the PCB there, and used a fuse carrier. Well, it's not a fuse carrier, it's a fuse with the wires soldered into the ends of the fuse, just on the off chance that the fuse would blow again, but it's touch wood, it's been okay since, just to keep everything nice and neat. This channel is actually disconnected during testing. So if I explain my test procedures, this channel is actually disconnected from the amplifier. The red and black cables are disconnected. The reason for that is because the auxiliary power supply needs 240 volts to provide power to the control, and the power supply during testing needs connecting to a variac and current meter and everything. So that's the yellow and blue cables going to the external rectifier there. Yeah, that's my test kit. There's a variac and a scope, audio precision, system 1, another scope for the output, a couple of multimeters, current meter there, scope. So I've got this multimeter on the bias for the amplifier module, but normally I would obviously test the switch mode power supply module and the amplifier module separately, but I'm going to attempt to do both at the same time in this video. The bias measurement points are on the low side. They're on the emitters, on the driver transistors there. So I'm measuring that as a voltage. It should be around 8 volts across the emitters, and on the high side I've been using these points here, which have got the black dots across the emitters on the other side of the amp, and there should be about 8 volts there too. So this preset is for the low side bias, and the preset for the high side bias is that one there. The output's currently connected to a 4 ohm dummy load in the corner of the workshop, and well, it's probably nearer 5 ohms actually, but it's near enough. And the other cables are going to the input of the analyzer, so we can see what's going on there. So first of all, I would apply power to the control section only. So during this power up, there will be no voltage applied to the switch mode power supply inputs. It's only applying power to the control, and by doing this we can see the behavior of the SMPS controller. So if I push this, I can show you the scope and we can see the clock speed. So that will start up. The oscillator is now in free run at 80k. So if this module wasn't already calibrated, then I would adjust the frequency to 80k clock rate before going any further, using that preset there, which is next to the red probe. So following on, the next thing I would do, well, actually I'll describe the channels on the scope. Channels 3 and 4 are the differential probes on the VDS on the power supply, and channel 2 is the current clamp. So basically what I would expect to happen as the variac is turned from 0 upwards is for a slight spike in current, but not too much. So yeah, the variac is currently on 0, so as I give that a little bit of voltage, you can see the VDS will increase straight away. And for instance, if there was a short circuit anywhere on the secondary side of the power supply or in the amplifier, then you would know straight away, because channel 2 would there would be a huge spike in current straight away. So by applying a couple of volts only, I think it's 32, but it would actually show from about 1 or 2 volts, you would know if there was a fault straight away. So it's very important to increase the voltage very slowly during the first testing. This is obviously not the first test of this module. So if we increase the voltage slowly, you can see the current will gradually increase. The capacitors are charging now. So I'll be watching the input voltage and the input current and the scope all at the same time. I'll be watching the VDS measurements for symmetry, and also to make sure there's no overlap. So the oscillator is still in free run at the moment. We will need to get up to quite a bit of input current for the oscillator to enter sync, and that won't happen until there's a load present. This is currently unloaded. So as we get past 120 volts, you can hear one of the relays click on in the amp. for the voltage selection on the power supply. So if we go past that, I'm always watching the current. The sine wave on channel 2 is obviously the very important one to watch, so if there's any misbehavior it will show up on that straight away. Okay, I'm now up to 245 volts and the amp is in idle. It's drawing 0.8 amps. That's just one side of the amp, by the way. I'm just testing one channel A at the moment. So what I would normally do is leave that for a bit before applying any load, but because the amp's already warm, this is the second test, we can do this straight away. So we look at my analyzer and generator screen. I would gradually apply a signal. Watch the screen. Because I'm testing the amplifier module and the power supply at the same time, I'm watching the distortion measurement there, so we can see the distortion is low, which is good on the output, and we can also see that the bias is still stable. So generally I would do a distortion sweep on the output at 1 watt. So if we go for that. So after that I would increase the output power to say 10 watts and repeat the sweep. You can watch the power supply at the same time, but you probably won't see any change in the current until we get up to a couple of 100 watts. So distortion is now very low at 10 watts output. And we can do another sweep. This is probably now measuring the realistic performance of the amplifier. You can see the distortion is extremely good now. Because we've got a bit of power now, we will see a rise in distortion as frequency increases due to the interaction between the dummy load and the output stage. I don't have any external Zabel network on the dummy load, so there will be some interaction. Okay, we can say that's very good. So I think next I will show the operation of the power supply as we increase the power quite considerably. So if I focus on the scope again and watch the current trace, and if I increase the signal level further, we can see the power supply gradually draw more current. So that's now 100 watts and the power supply is 1.5 amps. So generally, if all is well, I would carry on increasing that. And then what would happen on the power supply, it would start to enter sync. The controller would start to enter sync, and that happens at about 400 watts and probably about 3 amps. So you can see the waveforms are starting to change and the controller is hunting. So basically what's happening now is the controller chip is measuring the current being drawn at the output and adjusting the frequency accordingly for maximum efficiency. So this is where it starts to get interesting. The power is now 800 watts. It's safe to sort of edge the amp into clip. It's drawing now 5.2 amps. So what we're looking at now is basically any sign of distress on the measurements, and generally I would lose the 2 traces that we aren't really looking at now because they're happy, and that's channel 4 and 3. So this is the current clamp, and it's important to watch if there's any overlap, and I will demonstrate what happens if you adjust the synchronization. So at the moment I think that's about optimal. So I adjust the synchronization anti-clockwise. You can see there's a slight knee appears in the curve there, and so basically it's a case of adjusting the sync so there is no overlap, but the curve is quite smooth. So it's probably about there. If you push it too far, then the devices will conduct at the same time and blow up. So that's 5.2 amps. I normally do monitor the temperature too, but of course I've got my phone in one hand, so doing all this with one hand. We can watch all the measurements. That's 240 volts, that's the amp output. That's the distortion. It's now measuring 1 kilowatt into 4 ohms. So after a good soak, I would reduce the signal level first. Then you can watch the current return. Then reduce the input voltage. And that's the test complete. Right, this is part 2 of the testing where the power supply is reconnected to the amplifier as it would be normally. So the red and black leads from the internal rectifiers are connected to the lower PCB. There's a bit of a change in the test setup. Obviously the external rectifier is not connected. I'm monitoring the current now instead, going into the rear of the amplifier. I'm monitoring the DC bus voltage on that meter, and I'm monitoring the amplifier DC rails on that meter, and I'm monitoring the SMPS bus on this meter. So the important things here are that we need to be careful about the startup sequence. So it's important to test the soft start circuits before recommissioning the repaired module, because basically the module will start into effective short circuit when the variac isn't connected. So what I've done, I've implemented a kill switch and also a sort of a safe release switch. So that's connected to the shutdown terminal on the header, which is pin 1. So during the first test I would keep the shutdown held, and that would keep the controller chip out of operation until all the voltages and currents can be checked on the input. I've also got a system of discharging the bus capacitors there, which is just to dump the voltage, to prevent having to wait for the capacitors to discharge before testing the second time. So yeah, the scope is as before, so we can watch what's going on. What should happen, the scope is now in auto mode, so there's no delay, there's no trigger, so that will allow me to watch the behavior of the first few cycles when the amp first starts up into a short circuit. This is quite difficult to do with one hand, but I'll keep that held down. So what will happen is the bus will charge to 320. The controller isn't actually running yet, and the amplifier rails aren't yet powered up. I'm watching the input current there too. So essentially, when I release the switch on the shutdown, the controller will come alive and we can watch the first few cycles, and if anything looks wrong, then I've got a kill switch in my hand to shut the power down straight away. So if we release that, you can see his initial surge in the current, and then it stabilizes. And this is with no load on the amplifier output, it's only running idle, so the current is about 1 amp. And if I push the kill switch, it will immediately shut down. The amplifier DC rails will discharge quite quickly because there's a idle load there, but the SMPS bus will stay high. So we can repeat that test if I release. And kill. and then switch the amp off by the front panel. Now it's safe to use the other switch to discharge the SMPS. So that test essentially proves it's safe to probably readjust the synchronization, because I did leave it on the conservative side on this particular module, because I wasn't 100% sure what was going to happen during the cold start or the hard starting. So what I will do now is optimize the sync again, so it's a bit more efficient, and then recommission the module back into the amplifier for the final performance testing of the power amp module. Okay, this is the final loaded test before I put it all back together. It's actually up and running already. So at free run, the oscillator is at 80k, and what I've done externally is reduce the dummy load to 3.3 ohms, so we can draw slightly more current from the power supply. So if I increase the signal level, we can watch the current. Okay, that's now at 7 amps. And the frequency hasn't changed much, it's up to 81k, and I feel that's about right to leave that slight edge there. I don't want to push it too far. Okay, I'll now run through some performance testing of one of the amps which has been repaired, one of the EPC-780 amps. I generally start with frequency response and the level test. So before testing the amplifier module, I already know that the basic operation is okay. This is the final performance testing, so things like the bias and level, etc., has already been tested on the bench. So if we load up the frequency response test, the analyzer needs to know what the dummy load is, and currently it's 5 ohms in the corner. That is so the output wattage can be calculated. The industry standard way is to do it at 1 watts output, but I'm actually measuring these at 10 watts. So the first thing to do would be just to get a signal into the amplifier, and then immediately we can see the gain of the amp, which is just over 28 dB. So now the generator is running, we can regulate the output power to 10 watts and set the analyzer reference correctly, so that's F4 on the keyboard to do that. So now the graph should be at 0 basically. That's what dBr means, dB reference. So if we do a sweep,
It's important if we're comparing measurements with each other then to use the same test conditions. That's why the regulation is important. You can see in the lower chart there the previous measurements I've been doing on the 760 amps also, so I've been comparing them with each other. So that's the response into 10 watts. It's very good, right down to 10 Hertz and above 20k. If I enable some of these other measurements, you can compare the response between amps, and they're very tightly matched. So after I'm happy with that, I would move straight on to the distortion tests. First of all, distortion versus frequency. And again, we can see the previous test here. First of all, I would do it into a low power, say 10 watts again. It seems to be about the right starting point for these particular amps, and then I would do separate sweeps at a high power. So again, we would regulate to 10 watts. It's usually a good idea to decrease the signal level before starting the regulation. Yeah, so that's 10 watts. And just to double check everything's okay. It's worth mentioning that these screens are actually set up just for the BSS amps. You can see the file names there, BSS EPC. So this would be slightly different for different power amps under test. It wouldn't be very different, but for instance, I'm measuring the analyzer in decibel volts because that's what the specifications are, so it's easier to compare. So if we do a sweep now at 10 watts, the amp has had a preconditioned time of say half an hour, so it's the temperatures are stabilized basically, so we should get quite an accurate measurement. With the 780 amps, there's the output stage is in two halves. There's a low side and a high side. So as the output power increases, the distortion would increase when the high side of the amp kicks in. But because we're at 10 watts, we're on the low side currently, so distortion is very low. As the frequency increases above about 5k, I'd expect a little bump, and that's the interaction between the dummy load and the output stage of the amp. I could compensate for that externally, but I'm not doing that at the minute because I know it's not a problem. So when I've done the 10 watts, I would generally just increase that to 100 if all things are looking good, and then regulate again to that output power and repeat the sweep. This analyzer is actually capable of doing digital measurements, this FFT, using its DSP, but I like to do it the old-fashioned way, if you like, watching the sweep. Does take a bit longer, but it means the amp can be sort of soak tested at the same time, and any issues can be viewed in real time as they're happening. At a slightly higher output level, I'd expect a slightly higher distortion, so this is looking normal. Anything below 0.02% is within spec. So apart from the interaction with the dummy load, that's well within specification. So now I would load up frequency response, distortion versus amplitude is the next important one. So instead of sweeping the frequency, it would sweep the amplitude, and that would be measured out output power. So again, the analyzer needs to know the dummy load, which is 5 ohms currently, and this will show the distortion at separate output power levels, which is incredibly useful. So essentially this allows you to measure the output power of the amp, because it will show a sharp knee when the distortion gets into clip territory, and that's usually about 0.1. So yeah, if we regulate, actually we don't need to do that. I would generally run this test at a low frequency first, say 100 Hertz. Again, this has been done after a precondition period, so the amp's nice and warm. I'm watching for any signs of distress on the output power. Because of the amp design, it hands over to the high side. I think it's around 100 watts into 4 ohms. And then the amp will enter clip at around 1k. So I would then repeat that at, say, 1k frequency. And I expect a very similar trace. And also at high frequency, say 10k. I'd expect this to be slightly higher at low power, and then it will even off. So all being well, I would then compare that between amp modules. So if we look at some separate data which has been saved, this amp is serial 2099. So if we look at 2075, it's very similar.